This follows on from one yesterday where we talked about an overall review of StructureSolver. StructureSolver is intuitive and adaptable structural geology software. Software is used by a number of large oil companies, national oil companies, smaller companies, individual consultants, and also academic institutions. So our software is an interactive 2D structural analysis software that solves a lot of common seismic interpretation challenges and also helps us understand complex structural problems. We have three parts to the software: structural restoration, structural kinematic modeling, and area depth analysis. And you can do all of these together in a very flexible way. So today, I'm going to focus on two basin scale examples, hopefully get through both of them. The first one will be from the Sichuan Basin in China. Sichuan Basin is an interior basin in China with complex structural geology. The second one is the Quetzalcoatl extensional system in the Mexican Ridges Fold Belt. For the Sichuan Basin, we'll use a combination of area depth strain analysis and also component-based restoration of this dual detachment fold and thrust belt. And we'll compare the results from the restoration with the results from the area depth strain analysis. The Quetzalcoatl extensional system, if we get time to do that, we'll use modeling to establish correlations and timings across the structural fold belt. And we'll use link modeling and then again, area depth strain analysis to establish true structural balance. And one of the things that I'll be showing for both of these is how really, in many cases, in both extension and contraction, there's a mismatch between sort of naive line length balancing and actually true balancing, which involves an element of consideration of structural areas as well. So with that, I'm firstly going to review, because it's less familiar, I'm going to review the area depth strain analysis. We talked about this yesterday, but area depth strain analysis is a very powerful technique for analyzing interpreted geological or cross sections or geological or seismic cross sections. It uses the concept that in a pre-growth strata, the excess area of folds will diminish regularly downwards until it goes to zero at the depth of detachment. So you can think of a series of rugs on the floor and you push them from the side. The innermost rug will be folded in a very strong fold with very small area. The top rug will have a lot of area. The more you contract them, the more you push those rugs in, the greater the area will be. And there's a linear relationship between the area of individual folds and depth. And the slope of that area, versus depth curve. So here we've got area plotted with versus depth. The slope of this curve of area versus depth gives you accurately the true displacement on the structure. And you can understand that if you look at this area here, for example, is equal to this area down here is equal to this area, and there's a linear relationship between the height above the detachment and the excess area. So that's the standard theory for detachments, flat detachments that go into bedding, which is what we'll be doing today. Now, we also have ways of doing this where the detachments cross-cut the stratigraphy, and in that case, we can also estimate the dip and the position of the detachment as it cross-cuts the deeper stratigraphy. But in this, today we'll be looking at area depth analysis where the detachments are going into bedding and they're essentially flat or parallel to bedding, to regional bedding. So the second important thing that is really the crux of what the use of area depth today is that when we get the slope of area versus depth, we actually get an estimate out here from the edge of the section. We get an estimate of the true displacement in the section, in the structure, I mean. If we unfold an individual bed, in this case, this bed unfolds to here rather than out to the true displacement. What we're getting is a composition of the true displacement and whatever amount of internal strain that bed has experienced during the deformation. So in contractional structures, very typically, beds and layers will experience contractional strain. So the beds will actually, in certain parts of the structure, the beds will actually thicken up and the bed length will shorten. So if you take a naive measurement of the bed length and the shortened bed length and then flatten it out, it will not give you the true displacement on the structure. And by comparing what we call the nominal displacement curve, which is what we get when we flatten out the bed length, with the true displacement, which is what we get from the slope of the area depth curve, we can get a measure by comparing these two. We can get a measure of the layer parallel strain expressed as a percentage of the true original bed length. So that's something that a very critical point. And this theory was developed by Professor Richard Groshong. And we're finding pretty much every contractional structure, every extensional structure, when we look at it in detail, we see these disparities between restored bed lengths and true displacements measured from area depth. And that tells you a lot about the structure and tells you about internal strain within units and so on. So just to show you this example here, so what we were showing here was a sandbox model of a contractional structure where there was an imposed ramp here, and the hanging wall was moved up over the ramp by contraction from the left-hand side. So we actually know the true contraction, and all of the beds experience the same contraction. If we look at the area depth, if we create an area depth curve for this one, we can easily do that just by going through this little dialogue. We're going to say we select these beds one at a time, and that's planimetering now the areas of each of those beds. So you can see above the regional, so you can see the bottom one here. Let me just turn the display off so you hide the image. The bottom one is a small area. As we move up, the areas get bigger and bigger and bigger and bigger and bigger. And the areas are being plotted on this curve here of area horizontally versus depth vertically. So where that area goes to 0 is the detachment. And so we're accurately figuring out where the detachment is. And the slope of that line there is giving us out here this true vectorial displacement, 1147 millimeters in this case, which is giving us, for each of these beds, we're getting the same, because we're taking the slope of this, in total we get the same displacement, 1147. But if we look at where the beds flatten out to, which is given by this little tick here, if we just create a new little curve category, just to show that, you'll see that the bed, sorry, I'm using a beta version of the software at the moment with some improvements, and I've actually created a slight error in my area depthing where I lose the area depth occasionally. But so if I draw that marker, you'll see that this, gosh, it is a real problem. Okay. Undo. Okay. You'll see that curve shown there is the curve of the displacement estimated from the line length, okay? And so the deeper beds here have undergone shortening during compression, so they no longer go out to their true displacement. And you can see that you can see the thickness, for example, of these beds here. If we look at let's just turn on make them opaque just so you can see them. You'll see the thickness of this yellow unit, for example, gets a lot thicker in the core of the fold compared with its regional thickness. So that thickening is indicative of the layer parallel shortening, and the layer parallel strain is about 14% So the 14% is the difference between this tick here and the true displacement on that bed. Anyway, so I hope that makes sense. So that will be important for the example that we're showing in the next example from the Sichuan Basin. So that's just some background. And so let's now look at the real geology here. So this is a section from the Sichuan Basin in China. This section actually came from Petróleo, directly exported from Petróleo. So if we look at here, we'll see that it was exported from a time section, an inline in Petróleo. We're not currently connected to Petróleo, but if we were back in Petróleo, we could actually get live updates to it. If we look at, we've just got a little sort of base map here just to indicate where it is. And if we look at locating within the section, you could see that we've got the inline index, the crossline index, the inline crossline trace index, everything like that, and the X and Y coordinates all coming from Petróleo for that case. So this is, you know, quite high density seismic data. We're looking at it at a rather compressed scale here, but it is 1-to-1 with no vertical exaggeration in this particular case. So let me just show the interpretation dashboard, and you can see if we can color all of our interpretation here. So we've got a number of horizons interpreted plus faults. And here you can see these two bright pink units, two separate evaporites. There's a Precambrian evaporite down here, and then there's a Triassic evaporite up here. So we have a Paleozoic fold train sliding on the Precambrian evaporite, and then over the top we've got a Mesozoic through Tertiary set of strata folding on a Triassic evaporite. And there's a complete sort of structural disconformity between the lower fold train and the upper fold train. And so we can sort of do a variety of things. First of all, I'll just say that this coloring is fully interactive. So if, for example, we modify, drag something around here, for example, then we're interactively modifying the coloring on an instantaneous basis. So all of that computation of intersections between faults and horizons and everything is being done fully interactively. So again, I mean, if I move this around here, I'll change the intersections and so on and so forth. So that's a pretty nice feature. So the other thing that would help in this interpretation, most of it came from Petróleo. We had to continue into the air here, and we have a function called add a projected horizon. So we can pick on an individual horizon here, like this one, an interpreted horizon. We could add an additional flexural slip horizon. So in that case, I have to put a pinpoint in somewhere, and then I can just add projected horizons in. If I click them, they'll be added into the section. I won't do that, but you can see I can go up here. So that this upper fold train is all pretty much conformable in terms of flexural slip until we get down to the bottom in this blue unit here, but certainly through the green to the upper part, and we've used some of that technology to project the last part of the geology above the surface there. But if we come down and do the same thing in the lower section, you'll see that, for instance, if I project this one by flexural slip, it's okay for a while, but then it starts to cut across. So for example, there's thickening within that unit, and that unit, that orange unit there, is a Silurian shale. So that is not obeying fully clean flexural slip deformation. You can see that. So again, if we look at maybe down here, this green unit, which will be important in analysis, that's a Precambrian limestone or a Precambrian carbonate. And it is actually reasonably conformable. let's see, sorry, I did. So I'm going to do flexural slip. You can see it's reasonably conformal down to the detachment and apparently a bit above it. But it's quite detached from, again, it's discordant from this structure up here. So with that preamble, what we can do is, it's clear there's two fold trains. We can actually use area depth to analyze aspects of what's going on with these folds here. So in a similar way. So let's just go to our dashboard. We'll take the top units here, and I'll just change the fill opacity to 0 for them. So they disappear and we simplify things. So now we're looking at the bottom fold train. And so we're going to create an area depth graph. And again, detachment solving. We'll configure and we'll look at these, and then there. So it's pretty accurately picked the detachment. Here it's showing that the displacement, the overall contraction is about 4.5 kilometers. But if you look at the individual bed lengths, the bed length of the top of the Silurian shale actually is way back here. So the bed length there is a lot shorter than the true displacement, which is actually measured from the slope here. And likewise for these units here. But when we get to the Precambrian carbonate, because it's a non-ductile unit, its bed length is actually very close to the estimated area depth displacement of 4.5 or 4.6 kilometers. So here we've got a displacement of about less than probably about 2.5 kilometers measured from line length, and here we've got over 4 kilometers on this lower unit. So we're working on the assumption this lower unit is all part of the same structural styles, or sliding between these two evaporites. So now let's look at the upper unit. And I'll turn off these ones. So just to recap, here we've got about nearly 4.6 kilometers of true displacement, but only about 2 kilometers of apparent line length shortening on these upper units here. But we get the right length for this more competent carbonate down here. And that's consistent with the fact that, we saw this discordance between flexural slip projection and true actual structural development in the Silurian shale here. So let's look at this upper unit. So let's now, just in our area depth, we're going to we'll remove these units, these beds, and we'll add these ones. This one's there. So in this case, here we've got about 1 kilometer of shortening. So there's a lot less shortening in the upper fold train than there is in the lower fold train. We've got about 950 meters. But the bed length displacement is pretty much consistent with the area depth displacement. So we've got very little internal strain in these beds here, whereas there's quite a lot of internal strain in these beds down here. So just bear in mind here, we've got about 1 kilometer here with very little internal strain. We've got about 4.5 kilometers down here, but with a significant amount of layer parallel shortening within the upper units here. So with that, let's just we'll delete the area depth graph for time on. And now let's actually go about, and I'll put these detachments back here a little bit stronger color. Just for Sorry, 15. So now we can actually do some restorations on this. So let's, first of all, because we know this upper unit is largely conformable, at least down to the blue horizon, let's, under our interpret function, we'll create a marker from curved segments. So we can just use existing interpretation. We'll go down the edge of the structure here, go across, down that fault, across there, up that fault, there to that one, up that fault, because across, down, across, down. So we've used existing interpretations to create a perfect outline around this chunk of geology. So now we can create and drag the structural component from there down to here. So, and I've done some previous work down here, which I'll get to later. But so here's our structural component of that upper unit. And we can actually do a flexural slip restoration of that unit in one go. Let's just move it slightly off to the left side here. So this is now live with all its interpretation. So we can restore that. So I'll click on that bed as the restoration template. I'll use flexural slip. I'll go above and below. I'll put a pin line out here somewhere in the syncline. So here we're going above and then down to about there. And this takes a bit, there's quite a bit of computation involved in this. But we're restoring the seismic data along with, so there now is the restored unit. And you can see it restores, if we look at that, if you remember that length here, that's about 970, 920. We had 950 meters of true displacement from the original from the area depth. So that's consistent with the area depth analysis, and this is our restored seismic data along with the interpretation from that unit. So that's showing the restoration of the upper unit. Now, when it comes to the Paleozoic section, we can't restore that in one go because it's just too complicated. So what we have to do then is create individual little pieces. So if we focus on this Silurian shale, for example, we could just create a marker from a curved segment here, take that, take that, take that, and then take that out there somewhere. I'll just put it down here for the time being. And now we've got that little component, and then we can restore that component individually. So I've done that process. I've recreated that Silurian shale down here as individual components. I've then used the group structural component function to group them all together. So if you look at this, they're all still individual pieces. I could move that. I can do Control Z, get them back, but I can also, because they're grouped, I can drag the whole group around together, which is very nice. And then I can also copy and drag the whole group. So then what we can do is we can take those individual components and restore them one by one, which is what I've done down here. So just to illustrate the process of that, if I were to copy and drag, say, this guy, right? And I want to restore him to this unit here, then what I've got to do is I've got to actually extend my reference horizon a little bit, particularly on this side here where and I'll probably do it something like that, and it's there. And then I can use that as a template for restoration. So at that point, I can restore that individual component, and I'll use flexural slip. I'll restore above, in this case, just above. I'll put my pinpoint in the syncline here, and I'll come up, and I've then restored that little unit there. So that's got me the same thing. If I drag that, that's that piece there, right? So I'll just delete that guy. So I've done that with all of these units from right to left, and I've restored them all. And you'll notice when you restore them in that way, two things. One is if I put a regional line in here that is at the thickness outside of the core of the main fold through, and then a lot of these units have got excess thickness above that regional thickness line. And secondly, where coming back to the area depth, it does not restore. It restores to about 2.5 kilometers. Yeah, bit over, 2.5 kilometers relative to the end of the section here. So that's consistent with the area depth line length things that we got before. So we've got two things. We've got excess thickness, and we haven't got enough shortening. Now, if we do the same thing down here with the Precambrian carbonate, we do the same thing. We create little components, we move them down here, and then we restore them by flexural slip. You'll see that they restore out here, and they restore to about 4.5 kilometers of shortening. So that's consistent with the area depth estimate for the entire lower fold train. So how do we go about reconciling this unit here with these thicknesses here? Well, obviously, we've got to get rid of this excess thickening here. So that's where we have additional tools. So let me just copy and drag the whole structural component group down here. So to give me a new sorry, I just did copy. Sorry, copy and drag. So I'll create a new copy of it. And then let me sort of move it. I'll drag it off to the left a little bit. Give a bit of space, and then I'll drag this component back. So that's our base. I'll drag that back to the edge of the section. So let's look at this first component here. So it's obviously too thick. So if we drag that roughly into where it's going to end up here, then we have a function where we can apply pure shear to that thing. So we can stretch that structural component. And we do that in real time with the seismic data. So we stretch that, and we're keeping the area constant. So as we increase the horizontal stretch factor, the vertical stretch factor is getting small. So we get that to about that. So that's got about 1.3. It's got about 30% stretching in that. So at that point, we can move that to here, and we've got the right thickness. But now we have a disparity between between the fold angle here and the fold angle from this component here. So at that point, we can then shear that. So we're applying two consecutive transformations. We can shear that into, and then move that into here, right? So now we've restored these things. We've got the right thickness. We've got, and then we continue to do that same function with the next one. So, and this takes about 20 minutes or so to do all of those or less, and we're preserving all of the seismic data at the same time. So let me I'm just going to delete all of these ones here. And then hidden beneath here, I've got the results of that analysis, where I've taken all of those units and then stretched them out and sheared them. And at the end, I've got a small amount of residual shear, but not too much. Basically, the whole thing fits together pretty well. We've got a little bit of additional thickening in that unit that we didn't get out completely. We perhaps should have, made that into two components and divided it up somewhere in here in order to get the differential thickening in that last bit of it. But what's interesting now is at this point, the thickening, the overall contraction or the overall deformation associated with this bed matches both the Precambrian carbonate and also the area depth analysis. So just going back to the area depth, I'll just create if we create the area depth again, and I do it the bottom one. So this line here coming down from here is the true displacement. These points here are the line lengths, which match up with the naive restoration of that unit. This one matches up with the extra retrodeformation and also with the Precambrian carbonate. And then if we look at get rid of those ones, and we look at this one, we've got about 950 meters of true displacement, which matches the edge of this thing, and we've got very little internal shear internal strain within these units. So what I've tried to show you here is how we can do pretty quickly. We can do a relatively sophisticated analysis of this quite complex structure, and everything is fully interactive. We can undo and everything. And the other neat thing is the history of these things is completely contained. So if I, for example, I can locate within a structural component down here, and it'll show me where it comes from up in the original section. I can also, I could create a component out of all of these things and make that a single unit. I could also introduce new interpretation down here at any stage of the interpretation, any stage of the analysis, and propagate that all the way back up to the original section. So let's just add a new horizon. Maybe I'll make it bright pink. And I'm going to draw that horizon down here across this final set of restored. So for instance, we might actually see, sorry, let me first create a new component out of this entire component here. So to make it one unit will be simpler. So I can do that by easiest way is just actually draw something around it rather than going through the other thing. But if I just create a new curve category here of a marker, and I'll draw that around this entire unit here. And then I create and drag that. And that is now a single component. And composed of all of those guys. And if we look at the information for that one, now we can get lots of information. We can see the total area of it, for example. We can see all of its history of how it was created, and we can also see where it came from in all of these things. So again, here each one is showing the history. So if we then draw something on that one, so a new curve category here of, click on that horizon, make that active, and I'll draw a new horizon across this entire guy. Now bear in mind we're very zoomed out here, so we're not seeing that will attach to that structural component. And then I can transfer curves. I can send that component curve back to the section. So I'll set that, and that tree there that's coming up automatically is showing you exactly where the history of that thing came from. And so when we do that, that interpretation is being transferred all the way back from this component back to the original section. It's being broken up across faults all automatically, and it's being inserted into the stratigraphic column so that we've got now coloring from that unit as well. So let's just turn. Yeah, so we get the coloring back in that. So that's what that's telling you, is that all of that tracking, in order to get back from here, I had to understand that this component was created out of all these components. These components were created by stretching these components. These components were created by restoring these components, and those components came from the original section. So all of that history is being preserved. And then we could actually, if I sort of hid this component down here, and then I said I wanted to send section curves back down to components, I can send that down to all of the these components, and then I can turn the component layer fill on, and I'll see all the components now have been color filled. Okay, so we have a lot of transferability between the things. So I don't know, I think this is taking a little longer than I'd hoped, so I'm not sure that I can get to the other example. So maybe, Daniel, I should just stop at this point and take some questions at this point. Hopefully you can see the flexibility of how you can use this in complex fold and thrust belts, and very quickly and rapidly do a lot of things with the interpretation, and also with the seismic data itself. So you can see here we've got all of the seismic data in all of these things preserved very nicely. So any questions? Hi, Daniel.
Si tienen alguna pregunta, por favor pueden usar el micrófono o escribirlas en el chat.
So,
todo bien, all good.
All good, all good. Hopefully you understand. I mean, the key takeaway is it's you do a clean interpretation of your original section with faults and horizons, then it's very simple to break pieces out of it. You don't have to do anything fancy. You just have to use existing parts of your interpretation. Then once you've got those structural components, you can easily transform them. You can stretch them. You can shear them. You can restore them. You can also rotate them, which is another useful thing. What I haven't shown here is the transform to target. You can transform these individual components to target. I showed yesterday how to do that. There's also website examples for that. And so I could rotate, I could rotate that final, so I could rotate that guy, for example. And the other thing, when we have a final, for instance, if I wanted to take this guy here, which is one restored component, I can actually create a new section from that. Oh, sorry, this is not, as I say, I'm working with my beta version of version 6.0, and I've introduced a few little bugs into it. But you can take this this section here, this component here, and instantly turn that into a new complete section. So it's as if you had a section all by itself that just had that component in it. If you want to go further, so that it's very easy to do, like multi-step processes in this software. So anyway, hopefully that's useful to people.
Can you restore the sections with a try-share algorithm?
Actually, that's a good question. We cannot restore with try-share, unfortunately. The only, the way to restore with, to try-share is you've got to sort of essentially backtrack you have to model it in advance and then completely use the model parameters in order to take the try-share out, because the try-share is quite a, try-share is quite a complex deformation. So retro-deforming try-shear is actually more difficult than retro-deforming. We can retro-deform with inclined shear, with vertical shear, and with flexural slip. My approach to that generally would be to take different parts of the fold and then use slightly different mechanisms in each of them in order to approximate a try-shear, a retro deformation of try-shear. That's a good question. And of course, in some cases like these, this case here, where you have ductile deformation, you have deformation which doesn't follow any particular obvious algorithmic style of deformation. So you have to retro-deform it using a series of approximations, because otherwise you need a separate theory for every type, type of deformation. Does that answer the question? Oh, good, thanks. Okay, well, thank you. Thank you for everybody's attention.
Muchas gracias a todos por la atención. Como siempre, nosotros pues los invitamos a que usen estas aplicaciones que son muy útiles, son generalmente más económicas que la competencia. Nosotros tenemos soporte en Colombia, en Bogotá, y pues los invitamos a que mañana, por favor, sigan asistiendo. Tenemos 4 conferencias mañana. Y pues ojalá puedan asistir y estar con nosotros. También volverlos a invitar a que hagan su avatar y nos visiten en el stand. Y mil gracias a todos por la asistencia.
And I should just say one more thing. I had a couple of small bugs here, and when our release versions always are very bug-free, as much as we can possibly do, and we get complimented on how reliable the software is. But I'm in the process of just adding some functionality, and when I was doing that, I introduced a couple of bugs which we haven't yet tested out of the system, but I always try and demo with the latest version, just to ensure that it's a good way of testing things. So anyway, so